So, good morning, everyone. Good morning, Dr. Timir Karmakar. I welcome you to our webinar, weekly webinar from our university, SOA deemed to be university. And dear teachers, let me introduce Dr. Timir Karmakar to you, all of you. Uh, he is a MSc and PhD from IIT Kharagpur, and his research area is flow through anisotropic porous media. After completing his PhD in 2019, Dr. Karmakar worked as a project assistant and postdoctoral research associate at IIT Kharagpur for 1 year. He qualified for GATE in 2013 and CSIR NET in 2014. Dr. Karmakar has published 11 articles in reputed journals such as Physics of Fluids, Journal of Fluid Mechanics, Proceedings of Royal Society, a Journal of Engineering Mathematics, etc. He has attended several national and international conferences, and also he is a life member of professional bodies like Indian Society of Theoretical and Applied Mechanics and Indian Mathematical Society. And today, Dr. Karmakar is going to deliver his talk on modeling mechanics of lifting a large object from the seabed. So I think because many of the teachers from our department belong to the fluid dynamics area, so they will enjoy this talk, and as well as other teachers also enjoy this talk. So Dr. Timir Karmakar, I request you to start your the talk today.
Thank you, madam, for your introduction. Just let me share my PPT. Is this visible?
Yeah.
Okay. Okay. So, a very good morning to everyone. So, today my talk is about modeling mechanics of lifting a large object from a seabed. So, as you see from the title itself, that in this talk I will talk about the mechanics of lifting object from a seabed. Okay, so basically uh, I'll talk about these things. First, I'll introduce how to model and understand the physics of the problem and identify the corresponding physical laws. And then we'll talk about geometry, what kind of geometrical shape we can actually extricate it from the seabed. And then we'll fix some sort of boundary conditions depending on the geometry. And then we'll discuss little bit about the method. How can we deal the corresponding problem analytically or semi-analytically or numerically? Okay. And then at last we'll discuss some useful physical interpretation based on the physics. Okay. So this kind of, so as you can see, so this is basically uh, uh, lifting a object. So this is the colossal statue of Ptolemy. This is long time ago. It was actually sunken in the seabed. Now recently it has been actually extricated from the seabed. So now, what are the actually difficulties to if we want to object this kind of object from the porous seabed? Okay, so this is a cartoon diagram I've given. So this is generally it is lifted up from uh, by giving an vertical force or vertical velocity. Or even though by looking at the geometry it seems easy, but this lifting this object may last several days in trial, even it may become sometime impossible. Okay, so there are very much means difficulties associated with this phenomena. So this lifting an object up, okay, from this porous seabed. So this phenomena we call it as breakout phenomena. Okay, so more motivation we can actually get from this kind of thing. Suppose you want to salvage a sunken ships, okay, which is initially rest at the seabed. Okay, then how can we lift this object up from this seabed? Okay, so this also involves some difficulty, like how much time we require to lift this object up, or how much force we may need, what will be the requirements. Okay, that means how can we lift the object up without breaking it, okay, as it is. So there are some several difficulties. How can we lift this object or extricate this object without having any damage to it? Okay, and also, for example, suppose a submarine is at rest on the seabed. Now, when it will move, it has to detach itself from the seabed. Okay, then only it can move. Okay, so in submarine technology, this is a very actually uh, useful thing, that if we have an idea about the time duration, okay, that it may need this much time, then a priori estimate if we can get, then accordingly this will help us in submarine technology. That means we have a priori idea that within this time we can move, okay, or within this time we can detach itself from the porous bed. Okay, so these are the some motivation to attempt this work. Now, what are the key challenges? Okay, so as I discussed, the our aim will be always to reduce the overall risk and the safeguard personnel during the lifting operation, and also to improve the integrity and efficiency of the equipment throughout its lifetime. That means our aim will be always how can we remove, extricate or detach the object from the porous seabed, okay, without damaging it. Okay, so as so means without damaging it, with less time or less force, how can we lift this object up? So always that will be our aim. So as we discussed that sewage is basically porous in nature. Okay, so based on the properties of the seabed, okay, or rather the characteristics of the soil, okay, that form the seabed. So this force, how much force, okay, that we call breakout force, and how much time we require, so that we call breakout time. So that will depends on the properties of the soil. The soil, that means that is basically a porous medium. Okay, so that porous medium actually helps us to determine the breakout time and breakout force. Okay, so if we can get a priori idea about the breakout force and breakout time, then we can actually arrange the equipments or the security personnel accordingly, so that we can remove the object up. So for example, this is the Lord Buddha statue, okay, that is recently actually salvaged from the seabed. Okay, this takes place in Hussain Nagar Lake, this Hyderabad. Okay, so breakout time in this process it took 32 hours. Okay, so in this case the breakout time was, okay, 32 hours. Okay, so our means aim will be always how can we lift this object up, okay, without breaking it, uh, with less time and less force. That means our aim will be always to reduce the breakout time and breakout force. So as I discussed, these two important properties will be the porosity and permeability. Okay, so if we have an idea about the soil characteristics of the seabed, then that will make our life easier. Okay, so for that we need to know about these two important factors that will influence the total, okay, this breakout phenomena. So one of them is porosity. So porosity is nothing much. It is nothing that the pore space or how much void space is there. So it may be in a rock, it may be in a soil or any in means grains or cavities, fracture. Okay. So how much space it is occupied, okay, within the total volume. So that is called the porosity. Okay. And then now the permeability is the measure of ease at which the fluid can penetrate, okay, the ability to penetrate the medium. So it is called the permeability. Now by looking at these two, so you might feel that higher porosity always will imply higher permeability. Okay. From the definition, it looks like that, but it is not always true. These are two different things. So for the permeability, to getting a permeable media, we need the pores to be connected. Okay. So even though the porosity is large, it may not be imply that your permeability will be large. Okay. Why? Because you can see this picture. So in this case, okay, in the middle region, if you look at it, so you will see there are some pore spaces saturated with the fluid. Okay. But here the pores are not connected. Okay. So that means fluid cannot pass through these pores. So even though the porosity is present, okay, but permeability is totally zero. Okay. So this is porous, even though this is porous but non-permeable. Okay. But if the pores are connected, then we can say, so this permeability will be also there. For example, this picture, you can see that here the pores. So here some spaces are there void, and then it stopped, here also stopped. So this, even though this represents high porosity, but the medium is very low permeable. But in this case, since the pore spaces are connected, so we can say that this is a high porosity porous medium as well as high permeability. So these are the two important factors that will impact this breakout phenomena or this lifting the object from the seabed. So if we have a primary idea about the seabed, about the porosity of the seabed and the permeability of the seabed, then it will actually help us very much, okay, to get an idea about the breakout force and breakout phenomena. Okay. So I will talk about this in the forthcoming slides. So not only the soil, so it may means we come across porous media in our real life also. So suppose human body, so it consists of a human lung, so that is also a porous medium. Okay. And human knee joint. Okay. So knee joint, here porous media play a big role, that how much time we can actually stand comfortably. Okay. So in this case, between two knee joint, one porous coating is there. So this is called a cartilage. Okay. So there is a fluid in the gap, we call it as synovial fluid. So we can stand comfortably up to how that much time when it is remains fluid lubricated. Okay. When this fluid is squeezed out, then these two knee will means two joint will come close together and we feel pain. So this porous coating, okay, helps us to means to stand comfortably for a larger duration of time. So these are the actually example of porous media in real life also. So now we'll classify the porous media into several types. So these are mainly four types of porous media. One is homogeneous. Okay. So homogeneous means permeability is actually uniformly distributed. Okay. It depends. It does not depend on the position. It remains means uniformly distributed. And heterogeneous permeability means it depends on the position. So if we change the position of the porous medium, accordingly the permeability will change. And isotopic permeability is, so iso means equals. Okay. So if the permeability remains equal in all the directions, then we call it as isotopic permeability. And if it remains dependent on the direction, okay. So suppose if we move in x direction, we have a permeability. If we move y direction, we have different permeability. It is not equal. It depends on the direction. Then we call it as anisotropic permeability. So in real life, we will get the fourth one very much, okay, because the permeability in most of the porous media, the permeability will depend on the direction, okay. So in this work also, we will talk about this anisotropic permeability and how it impact the total breakout process or the lifting process from the porous seabed, okay. So now heterogeneity and anisotropy. So heterogeneity, as I discussed, this depends on the position, and anisotropy means it depends on the direction. Okay. So I want to give one example. Suppose you want to cut wood, okay, along its grain. Okay. So if you want to cut wood along its grain, you can cut it easily. But if you want to cut the woods opposite to its grain, then you require much force. Okay. So that wood can be considered as anisotropic media. So it does not mean that the permeability will be always anisotropy. Okay. For porous media, permeability is the main factor. So that for porous media, your permeability will be direction dependent. But anisotropy is a general thing. It may depends on your diffusivity, any materialistic property. Okay, so any materialistic property, if it depends on the direction, then we call it as anisotropic porous media. For example, if you look at this picture, so this means rock is formed horizontally layered formation. Okay, so that means if we put water, then it can pass horizontal direction easily than the vertical direction. Okay, so in this case, horizontal permeability will be larger than the vertical permeability. Okay, so this anisotropy actually occurs very much in most of the soil. Okay, so it will impact very much on any kind of properties or any kind of fluid mechanistic properties such as streamline velocity or the pressure, anything. So it will impact that property very much. Okay. So as I discussed, for anisotropic porous medium, permeability will be different in different direction, while for isotopic porous media, it is same in every direction. Okay. Now, what is the reason of anisotropy, or rather, what causes the anisotropy? Okay, in porous media. So anisotropy occurs due to the formation of soil or rock fracturation in different direction. Okay, that means if the porous media, it doesn't have any particular means formation. Okay, so if this is means the pore space are arbitrary oriented, it doesn't have any definite structure, it is arbitrary oriented, then we call it as anisotropy. So this is the one main reason of anisotropy. Okay. For example, as I discussed the above example, so horizontally layered sediment. Okay. So if the means your means that porous media, if it is horizontal layered, that means suppose you can actually make the anisotropic porous media also. Suppose if you give a sand layer, then above gravel layer, so layer. So if this can be formed, that total porous media we can call it as horizontal layer medium. Okay, so horizontally layer medium, your horizontal permeability will be larger than the vertical permeability. Okay, so like this, here you can say this is horizontally layered. So this sediment is formed with horizontally layered rock. So in this case, your horizontal permeability will be larger than the vertical permeability. Okay. So now this is one example. suppose if we take a cube and if we fill with spherical balls, then you can see that there will be gaps and fluid can penetrate through these gaps. Okay, so in this case, if you observe that it can actually penetrate the this medium, or fluid can pass through these gaps with equal ease in all the direction. Okay, so this will be independent of direction. So this can be considered as a isotropic porous media. But instead of sphere, if we take some means a cylindrical shape, then it will depends on the orientation of the cylinder. Okay, so this can be considered as an isotropic porous media. Okay, so these are the one of the main equation that governs the fluid flow inside porous media. So we call it as Darcy porous media. This is called the Darcy equation. This is obtained by Henry Darcy in 1856. Okay, so here this is the pressure gradient, this is the permeability of the porous media. So for isotopic porous media, this permeability is a constant, but for anisotropic porous media, it will be a tensor kind of thing. Okay, so here you can see, as I discussed, that permeability depend on the direction. So here Kij refers the permeability along the ith plane and jth direction. Then later on, some modification has been done by Henry Brinkman. So he has added this additional term, so that is called the Brinkman term. Okay, so this equation, Darcy equation, this doesn't include the viscous term, but Brinkman later on the modification has been done. Okay, so this also means include the Brinkman term, or justify the viscous effect. Okay, so anisotropic permeability matrix. So as I discussed, for the cylindrical shape, if we give a rotation phi, then it will be take form of this kind of matrix. Okay, so this is the typical structure of anisotropic porous media. Okay, so now coming to the problem. So as I discussed, the breakout phenomena. So the breakout phenomena is nothing but the full process of complete detachment of the object from the porous bed. Okay, so once we detach itself, the porous bed or the seabed, then we can call it that breakout occurs. Okay, so these are the some literature. Okay, so it moves chronologically towards complex model. So this is our work. So all these studies, okay, even few studies has been made, but a detailed knowledge about the breakout phenomena, okay, how much time it requires or how much force we need, so that is still a topics of discussion. Okay, so this is the suppose object, and this is the anisotropic porous bed. Okay, basically this is a seabed, so this is infinitely extended, it has no boundary. Okay, so the porous bed, we or the seabed, we assume that this is a porous in nature and also anisotropic. Okay, now this is the object, we want to lift it up from this porous seabed. Okay, so now we assume that the object is at neutrally buoyant condition. Okay, that means it is just sitting at rest above the seabed. Okay, that means it is not inside the seabed. Okay, just most of the sunken object will be like that only. It will just be at rest above the seabed. Okay, because it cannot go inside the porous media, because that seabed is basically low permeable in nature. Okay, so now neutrally buoyant means the buoyancy force is actually balanced by the weight of the object, so we don't have to actually worried about the buoyancy force and weight of the object, it is already balanced. Now what is we have to worried about, how can we overcome the suction force in this gap region. So when a object will be at rest above the seabed, so there will be a gap region, so that will be saturated with fluid. Okay, so initially this gap is very the means length of this gap is very, width of this gap is very small. Okay, sometimes it is actually even smaller than the interstices or the pore size of this medium. Okay, so there will be a suction force will play into account. So that amount of that suction force is very high. So once we overcome that suction force, then we can lift the object up. Okay, so here we, even though the object is very large, okay, we don't have to bother about the weight because it is already balanced by the buoyancy force, but this suction force is very high. So how can we overcome that suction force? Okay, so this basically occurs at the near the interface, so we call it as mud line. Okay, so this interface, that is the x-axis, we call it as mud line. So near the mud line the suction force will act. So how can we overcome this suction force? Okay, so definitely we have to give an upward force. Okay, so if we uh, uh, this upward force is greater than the suction force, then we can lift the object easily up. So one thing is that since the object is very large, its length is very, okay, L is very much larger than the width of this cap. Okay, so in this case we will assume that H is very smaller than L. Okay, so now there are two regions, as you can see. One is gap region, okay, that is basically the fluid region, and another is the porous region, okay, that is infinitely extended. So this double arrow represents that porous seabed is infinitely extended. Okay, so now in the gap region we assume that the flow is governed by Stokes equation, and in the porous region we assume that the flow is governed by Brinkman equation. So now here we have added an additional factor, that is the porosity. In general, in Brinkman equation, when we consider, so we assume phi equal to 1, but to actually one recent study, Chang et al., they have considered that if we consider the deformable porous media, okay, then it will have two phases, soil and means solid and liquid phases. So if we drop the solid phase, then only this means fluid phases will be there. So to contribute that, we have taken this phi. Okay, and this is the equation of continuity. Okay, so as I discussed that the uh, seabed, we assume that it is anisotropic in nature. Okay, so it definitely, if we consider this two-dimensional thing, so it will be a 2x2 matrix. Okay, where K1 and K2, K1 is the permeability in the horizontal direction and K2 is the permeability in the vertical direction. Okay,
Dr. Karmakar,
yes,
could you please go to the last slide? Sorry for the interruption.
yeah.
Why you have considered an effective viscosity?
Yeah, effective viscosity, actually effective viscosity and fluid dynamic viscosity, these are not in general equal if we discuss about the porous media. So this effective viscosity will depend on the porous media. Okay, so if we change the porous media, so accordingly the effective viscosity will change. So definitely there is a relation between the effective viscosity and the fluid dynamic viscosity. Okay, so to focus into that, we have discussed, means we have taken this different. Okay,
Okay, thank you.
okay, so this is the typical geometry. Okay, so this is the object and everything is happening near the mud line, that is nothing but the interface. Okay, so what are the boundary conditions? We assume that this object bottom is means impermeable, so no flow penetrates, and we assume this symmetry. So this is a slightly relaxed assumption. This may not be in general a symmetric configuration, but for this work we have assumed that this configuration is symmetry, and at the liquid porous interface, that is the mud line, okay, or rather the seabed, okay, we assume that here the momentum exchange is happening, so we assume here the continuity of stress and velocities. Okay, so now if we introduce the non-dimensional variable with that equation, so we can get this kind of variable. So here the two important, most of the important factors, this epsilon, h by L. So that is the width of the gap. Okay, so that we have considered very, very less, because when the object will be sitting at rest above the seabed, so the obviously this gap will be very, very less. And dx is the means non-dimensional permeability is along x direction, dy is the permeability along the y direction, and this xi k2 by k1 is the anisotropic ratio. So k2 means the permeability in the vertical direction, and k1 means the permeability in the horizontal direction. So we'll see that this xi or the anisotropic ratio will very much affect on the breakout phenomenon. Okay. So as you can see from this geometry, okay, so when we give a upward force, so the width of this gap will increase. Okay, so initially it is at rest, so the width of the gap is very less, but even though it is less, it is means some flow is there. So where this flow, actually fluid comes from? So this comes from vertically from the porous seabed. So once this we given means a uplift force or upward force, then this fluid will come vertically from to this region, and eventually it will saturate this region. So once we will increase the gap with more, then the flow from the peripheral region or the sea water, it will saturate this region, and eventually it will overcome the suction force, and then we can lift the object upwards. Okay, so here we can note that horizontal flux, those which is coming from peripheral region, or that is nothing but the water of the sea, okay, and vertical flux, so that is coming from vertically from the porous seabed. So these are the total flux. So if we assume the total flux is 100%, okay, so the from the peripheral region what is coming, so that is the horizontal flux, and from the vertical region what is coming, so that is the vertical flux. So this is the total flux. Okay, and as I discussed that what is the suction force. Okay, so that is our aim. If we overcome the suction force, our job is done. That means we can lift the object up. Okay, so the suction force or the lift up force is nothing but the applied to the bottom of the object in excess of the buoyant weight of the body. Okay, in excess means as we assume that the weight of the object is automatically balanced by the buoyancy force, so we don't have to actually bother about the weight of the object. So only we have to bother about the suction force. So that is nothing but the pore pressure which is generated near the interface or near the mud line. So if we can give, or we can give uplift force vertically which overcome this, okay, the suction force, then we can lift this object easily up. Okay, so the breakout force is opposite to the suction force. One has to overcome the suction force to lift an object up from the porous seabed. Okay, and the breakout time, the complete time taken for the complete detachment of the object from the bed. Okay, so breakout force and breakout time, this total phenomena is called the breakout phenomena. Okay, so we'll see first turning point. So when we will lift the object up, so slightly when we will increase the gap width, okay, so then flow from the periphery will come into account. Okay, so in that case the breakout or the lifting force will remain constant up to a certain gap width. Okay, then suddenly the peripheral, when will increase more gap width, then water from the sea will come into account, and then we can lift the object up. So that is called the second turning point or the breakout point. Okay, so in that case, suddenly it will detach itself, and accordingly our breakout force or the suction force will be reduces to 0. So this is the generally happening. So this is the means an object we want to lift up from this porous seabed, and we are giving a counterweight. So this will break out. Then the breakout force will be equal to the weight of this counterweight object. Okay, so these are some experiment has been done, okay, by May, okay, and we have compared our result to May et al, and we this shows a good agreement. And this is the force per unit area or the breakout force. So our aim will be always how can we reduce the this force per unit area or the breakout force. So this we can actually plot as the function of gap width. So we can see, okay, so as if we want to lift the object up with a higher vertical velocity, then of course we have to give larger amount force. Okay, so that's why we can see that the velocity increasing velocity results a higher amount of lifting force. Okay, and we can see here that up to this with, let us say, 10 to the power minus 2.5 or 2.7 kind of thing. So up to this remains almost constant. This curve is remain almost straight. That means this force remain almost constant. So this is called the first turning point. Okay, after that it is suddenly decreasing. Okay, and after some means time it will reduces to 0. Okay, so this is called the first breakout point, and when this force reduces to 0, then this is called the second turning point or the breakout point. Okay, so now as I discussed that the properties of the seabed or the soil characteristic will have a larger impact on the breakout phenomena. Okay, so depending on the porosity also or the permeability, it may change. Okay, for example, okay, if suppose seabed is consist of gravel, okay, so in that case permeability will be this, or if it is consist of silt or clay kind of thing, then the permeability will be this. Okay, so as you can see here, we have presented the force per unit area to lift the object up from the seabed. Okay, depends on the uh, properties of the soil. So here you can see that if we want to lift an object up from a gravel seabed, okay, then we need very less amount of force. But the same object, if we want to lift up from a silt or clay kind of porous bed, then we need a larger amount of force. So that's what, if we have a priori idea about the soil characteristic or the seabed, means what kind of seabed it is consist of silty clay or fine sand or gravel kind of thing, then we may have a priori idea about the breakout force. Okay, so our analysis means in this work will help to actually give a priori idea about the breakout force. And this is some comparison we have made with the previous studies. So Chang et al, they have done the work for isotopic porous media. That means they assume that the permeability is same along all the direction, but this is not means true in most of the cases, because seabed is generally horizontally layered formation. So definitely in that case, means horizontal permeability will be the larger than the vertical permeability. And also such cases are there when the vertical permeability is larger than the means horizontal permeability. So overall, this seabed cannot be actually isotropic. Okay, so generally it is anisotropic in nature. So as you can see, Xi is the anisotropic ratio, that is the vertical by horizontal. Okay, so if we increase the anisotropic ratio, or rather the vertical permeability, okay, then we will get the force per unit area is very less. Okay, the reason behind this is, if we increase the vertical permeability, okay, the upward flux, okay, that come from the porous bed will be larger. Okay, so once the upward flux is larger, it will saturate the porous media, it will saturate that gap. Okay, so once it will saturate the gap, the suction force will be reduced and we can lift the object easily up. So here we have see the impact of the anisotropy. So this is the isotropic case and the permeability is same. But if we take the vertical permeability larger, then we need less breakout force. And if we take horizontal permeability is larger than the vertical, then we need larger breakout force. Okay. So this is the flux. So if we assume that the total flux is 100%, okay, so then in that case, the here you can see, if we increase the vertical permeability, then more flow will come in the vertical direction. Accordingly, the horizontal flow will be less, because total flow, if we assume, or the total flux, if we assume 100%, then if more flow comes vertically, then obviously less flow will come horizontally. Okay, so this is the thing. So here the main thing is, if we increase the uh, vertical permeability, then we can lift the object easily up. Okay, so this is the actually the streamline looks like. So initially, if we see, when the gap width is very less, so as I discussed, where the flow comes from, it comes from vertically from the porous bed. So the streamline will be vertical, right? Okay, when the gap width is very less, suppose 10 to the power minus 3.5. Okay, now we slightly increase the gap width, 10 to the power minus 2.8. Then slightly means flow will come, okay, it will start coming from the peripheral region as well. So the streamline will be no more vertical, it will be slightly distorted towards the peripheral region. Okay, so as you can see, it is slightly distorting. That means in this region, your this sea water is also coming into account. Okay, it is no more vertical. Okay, then if we increase larger gap width, for example 10 to the power minus 1.5, then more flow will come from this peripheral region. Eventually the streamline will look like this kind of form. Okay, so this is the typical actually means flow phenomena happening near the interface. Okay, so now where these suction forces are effective, as we discussed, the suction forces are effective inside a thin layer. Okay, so if we do an order of magnitude analysis, we will see that this length is nothing but the boundary layer. Okay, we call it, for porous layer we call it as the thickness of the Brinkmann layer. Okay, so the Brinkmann layer thickness is of order of root k. Okay, where it is much effective. Okay, so we call it as a Brinkmann layer. So you can see, if we plot the velocity in the porous region, so outside, so in near the sea bed, okay, the distortion is happening much. Okay, outside this, it remains almost straight, so nothing much distortion is happening. So this phenomenon actually is very much effective inside a thin layer. We call it as Brinkmann layers. Okay, so these are the significant observation. We can actually conclude that before the first turning point, lift-off force remain almost constant, and after the first turning point, lift-off force decreases very rapidly and suddenly reduces to zero. At that point, we can tell that breakout occurs. That means we can lift the object up. Okay, and before the first turning point, that means when the pore flow vertically coming upwards, to saturate the gap. In such cases, the anisotropy of the soil play a significant role. Okay, and this is more details can be found in this work. So these are some references.
Sure. Any questions? Any
If there is,
questions?
yeah, if there is no question, I will ask a question.
Yeah. Thank you, Dr.
Uh,
Karmakar. Thank you for your nice presentation and talk on this topic. And so now I request our Dr. Avijit to offer the vote of thanks for this webinar.
Ma'am, before asking, giving vote of thanks, I would
Yeah,
like to ask one question from Dr. Timir
yeah,
Karmakar.
yeah. And that's why I told you. Yeah.
Yeah. So, Dr. Karmakar, could you please go to the slide of showing the pictures of streamlines?
Yes.
So, this epsilon data of this epsilon from which source you have taken this? From previous literature or where?
Yeah, this is taken from the previous literature, mostly in Chang et al. What I have discussed that they have considered the isotopic porous media. Okay, but they have done means experiment as well, and they have means collected the data from some literature. So in main thing is in this work we have the gap width we have assumed the same. Okay, order of the gap width is same. Only our focus was to the actually reinvestigate. You can say reinvestigating the work for the anisotropic porous media, as we feel that the anisotropy will have a larger impact on the breakout force and time. So the data we have used some sort of, you can say, from this work. Yeah.
And in the same slide, I can see that, sorry, yes, capital V equals to 2.3 into 10 to the power minus 5.
Hmm.
So is it not like it is negligible?
No, even though it seems so, you have to actually think means the reference frame where it is occurring. So if you want to lift an object up, you cannot give suddenly a higher vertical velocity. Okay, because it weight tons of metric tons of, right?
Okay.
So you have to actually, it is a very slow process. The lifting an object, it is not like that we can lift the object in hours. It may last several days in trial, even it may take months also. It is a very slow process. So the vertical velocity, even we impose a larger amount of vertical force, but suddenly it will impact the a negligible. You can means for this reference of frame, it is not negligible. But if you consider any other reference of frame, it might look negligible. But it is a very slow process. So this will also means it will move slowly upward and increase the gap width.
But the target is also to reduce the time, right?
Yes,
Breakout time. Hmm.
yes. So
So,
eventually, to means you will always want to lift that object up, right?
hmm,
So if
hmm,
you, even though it may take some larger time, but your aim will be how can we lift the object up without breaking it. So
breaking. Okay.
even though our aim will be to reduce the breakout time, but the main
Hmm.
thing is to lift when you extricate the object.
Okay. Thank you. Thank you, Dr. Karmakar, for this wonderful talk. So at the end of 14th Siksha Anusandhan weekly academic lecture, I, Dr. Ravi Sutradhar, the co-convener of this weekly series of webinars organized by the Center for Applied Mathematics and Computing, shall take a liberty of proposing vote of thanks. We thank the speaker, Dr. Timir Karmakar, whose talk has surely enriched our knowledge on anisotropic porous media and its permeability, which plays a significant role in fluid mechanics. Our thanks are due to the colleagues, scholars, and students in the audience. Our big thanks go to Dr. Manojanjan Nayak, the Honorable President of Siksha Anusandhan Dept University, who have been always a source of inspiration to all of us. I extend our thanks to Professor Manjula Das, the head of Center for Applied Mathematics and Computing, for the necessary supports. Lastly, I, on behalf of the Center for Applied Mathematics and Computing, Siksha Anusandhan Dept University, extend our heartfelt thanks to all. So thank you once again, Dr. Karmakar. Thank you,
Yeah.
madam, and thank you, colleagues.
Thank you. Thank you, Dr. Karmakar.
Mm,
Thank you,
yeah.
Abhijit.
Thank you, Dr. Abhijit Sutradhar, and
Thank you,
to
everyone.
Thank
organizing
you.
the committee for
Thank you.
inviting me. Yes,
Yeah.
thank you.
Thank you, colleagues and all students.
चलो हो गया थे
I'm officially ending the meeting here and
Okay.
ending the recording also. Thank you.
Acha.